Science. And welcome, ladies and gentlemen, to our first topic in Earth Science. Topic number 1, minerals. This week, we are going to be exploring some of these really cool things that we call minerals. So let's not waste any more time. Let's get right into our lesson on minerals. Be sure you're on the right page of your book for your lesson notes so that you can begin jotting down this important information on our topic, minerals. So here we go. Minerals. We saw some interesting videos yesterday. I took you on a little field trip to various places, and I'd like to take today to explore some of the information, more specifically summarize some of the things that you were introduced to yesterday, but I want you to make sure you have opportunity to write them down in your book. So be sure your book is open to the right page. Now, New Jersey oftentimes gets a bad rap, but as you'll be hearing me say over and over again throughout the year, New Jersey has got to be the coolest state in our country. We have such variety and diversity within our state. Our geology in particular is so varied, from the coastal plain of the Jersey Shore to the highlands and the ridge and valley, mountainous area in the northwestern part of the state, and everything in between. We have such variety packed into a small location. But this week we're talking about minerals. And not a lot of people may think about New Jersey when you think about minerals, but check out this map. This is a map of some of the abandoned mines that exist in New Jersey, and we have copper mines, graphite mines, iron, lead, magnetite, mica, sulfide, uranium, and zinc mines. All of these are various mines that we have had in our own state of New Jersey. Now, you'll notice most of them are red, which are iron mines. There are a lot of iron mines in New Jersey, or at least there have been in the past. And this is only showing the northern part of the state. In southern New Jersey, there's a lot of bog iron that was mined and utilized for various purposes in our state's history. But here's the deal. A couple things. Since there are so many mines in New Jersey, you might be tempted to find some of these mines and go explore them, but I'd like to caution you, don't do that. Unless there's a mine that's open for public use, don't go near abandoned mines. They could have very deep shafts, very dangerous roofs. They could collapse on you and kill you. So many of these mines today in New Jersey are on private lands, so be sure you stay away from mines. But here's the deal. Here's a couple of pictures here that I showed you yesterday in the video. This one is of the Pequari copper mine in Pequari Township in Warren County, New Jersey. This is an abandoned copper mine near the Delaware Water Gap. You can hike up there. It's gated off. You can't go into it, but you can hike up to it, and it's pretty cool. Here's another one locally known as Ice Cave outside of Phillipsburg in the Marble Hill Mountain area. And the Highlands Trail actually goes right by it, and you can actually explore this mine. It's a big open mine where iron used to be mined, and I mentioned that in yesterday's video. But in both of these cases, they were mined for minerals. So let's get into the nitty-gritty details about minerals and what exactly a mineral is. As you know from yesterday, minerals, in general terms, are naturally occurring inorganic solids that have a definite chemical composition and a crystal structure. That is the basic definition of a mineral. But we're going to be breaking this definition apart today in the first part of our lesson, and we're going to unpack each of these items in the definition one at a time. So let's begin with the 5 characteristics of minerals. And aren't these specimens really cool to look at? In fact, some of these specimens you can see here look very similar, I think, to the ones that we examined in the classroom yesterday for my own personal collection. By the end of the week, you might even be able to identify some of these minerals. But let's get to the 5 characteristics, which also are the definition, or is the definition of a mineral. Number 1, naturally occurring. And remember, be sure you are writing these notes down in your book. Remember, the red words on the screen are your cue for writing it down in your notes. So the first characteristic of a mineral is that it has to be naturally occurring, which simply means it has to be found in nature. It is not synthetic or produced in a factory. We have plenty of things that are produced in factories, manufactured by human hands, but in order to be a mineral, it's got to occur naturally. So if you can go outside and you can dig it out of the ground and it formed there initially, it's naturally occurring. That's why I have the beautiful picture there of a nice little waterfall in a pond, because when I think of nature, I think of peaceful flowing water. Water? Ooh, we'll get to water later on. So item number 1, characteristic number 1, naturally occurring. Number 2, it has to be inorganic. Now, when we say inorganic, we are suggesting that it is not formed by or from living things. Here we have a picture of a pet rock. This pet rock is not really a living thing. Back in the 1970s, when I was a kid, pet rocks were pretty popular for a little period of time. They seem to be becoming more popular these days. Again, things go in cycles. But a pet rock is great because you don't have to feed it because it isn't alive. But this pet rock is in the shape of an egg, kind of, and an eggshell, although an eggshell is naturally occurring, it's not inorganic. It's manufactured by a living thing, namely a chicken. So an eggshell would not be a mineral because it is organic, not inorganic. So in order to be a mineral, you've got to be naturally occurring and inorganic. The third characteristic is that it must be a solid, which simply means it's not a liquid and it's not a gas. It's not a different state of matter other than a solid. And solids have a definite shape and a definite volume. We watched a brief video yesterday and it questioned whether water was a mineral or not based on the definition of these 5 characteristics that we're reviewing. But think about it. Think about it as we explore the remainder of these characteristics of all minerals. But in order to be a mineral, naturally occurring, inorganic, and it must be a solid. And again, when we talk about solids, we're really talking about at room temperature. Room temperature, the temperature that we're at right now. Number 4, you must have a definite chemical composition. And that's kind of a technical term, but what it is saying is that a mineral must have a specific chemical formula, a certain set of ingredients, you might say, that are found within that mineral and that mineral alone. In order to be a different mineral, you got to have a different chemical composition. But here I have a chemical formula, H2O, which you are probably familiar with. This H2O, just say it out loud if you think you know what H2O is. Yeah, water. Water has a definite chemical composition. There are 2 atoms of hydrogen for every 1 atom of oxygen, and that's what a chemical formula indicates. It's basically like an ingredients list and a recipe all in one. So in order to be a mineral, got to be naturally occurring, inorganic, solid with a definite composition and crystal structure. This, I think, is really cool. When you look at my mineral collection over on the side of the lab there, you can see some of the different crystal structures, the different shapes on a macro scale, a scale that you can actually see with your eyes. But any crystal structure, like the pyrite I showed you here, this cubic crystal structure, is indicative or reveals the repeating pattern of atoms that exist within the mineral itself. So a mineral, because of its definite composition and because it's in a solid form, it will grow a certain shape of crystals. In fact, I just showed you a real specimen of pyrite. Here's a picture of pyrite in our notes right here. I just noticed that. And you can see that the crystal structure is cubic, these cube shapes. And different minerals, because they're different chemical composition, have different crystal structures. And we'll be exploring those throughout the week. So these are the 5 characteristics of minerals. Make sure you have them written clearly in your notes. But now I'd like to take those characteristics and go into our next phase here, which involves identifying minerals. Later in the week, we're going to be doing a lab activity, and in our lab, you are going to be trying to identify a number of unknown minerals. And you're going to be examining various characteristics or properties of minerals to help you identify them. So we're going to go over those right now, beginning with color. If you examined my mineral collection yesterday, you probably noticed there is quite a variety of different colors. And with minerals, there is an extreme variety. There is quite a diversity of different colors when it comes to minerals. In fact, many of our paint pigments actually come from different minerals. It's the mineral composition that gives many paints their unique colors. So I think that's very interesting. However, colors are very variable and unfortunately not very reliable when identifying unknown minerals. And I'm going to give you one example as to why that is the case. It might be the most obvious characteristic that pops out at you when looking at a mineral, but it can be very deceiving. Here's why. Here's one mineral, beryl. And if you look at it, there are different colors. There's red, orange, green, blue. There's all these different colors of beryl. And they're all the same mineral, even though they have many different colors. Just one itty bitty little change in the chemical composition and the introduction of a different element can totally change the color of a mineral, because minerals can have what are called impurities in them. And those impurities can trick you into thinking that the mineral is something that it actually is not. So as we try to identify minerals later this week, yes, we'll be looking at color, but I want you to remember that color is the least reliable characteristic. So let's move on to item number 2 on our list, and that is the luster. What in the world is luster, Buster? Well, luster is the way in which light reflects off the surface. Generally speaking, when we're talking about minerals, minerals can either appear either metallic or non-metallic. Metallic luster is like this sample of pyrite I have here. It looks like it's made up of a metal, Why? Because, well, it's got flat, shiny, very shiny surfaces that look like a metal. So if it looks like it's a shiny metal, then it has metallic luster. If it's dull or rough or doesn't look like a metal, then we would call that non metallic luster. So a mineral can either have metallic or non metallic luster. Keep that in mind. That can be a helpful characteristic or property when identifying minerals. Because when we do our lab activity on Thursday, we're going to be narrowing down the list of choices by eliminating certain minerals that don't possess certain characteristics like metallic or non-metallic luster. So here is, again, an illustration of different minerals that appear metallic on the top. Some good examples. We've got pyrite and galena and graphite here. All these minerals have a metallic luster. They look like they're shiny metals. And the ones down below here, well, do not. They look more like rocks than minerals, perhaps, to your eyes, because they do not reflect the light in the same way. All right, number 3. The third item on the list is hardness. And if you look at this picture here, you can probably guess that diamonds have something to do with hardness. And in fact, they do. Diamonds are known as the hardest mineral, but that doesn't mean diamonds can't be broken. Doesn't mean diamonds can't be cut. Diamonds are hard because they resist scratching, which is why they make wonderful gemstones on like engagement rings or jewelry, because diamonds resist scratching. I'm sure many of you have been scratched by different things, maybe your cat's nails or briars or pricker bushes in the woods, or maybe your sister's nails, I don't know. But you know what scratching is? Well, minerals can be scratched as well. Some minerals are much softer than other minerals. Some minerals can be scratched very easily. Other minerals, like diamonds, for instance, don't scratch very easily. And again, that's why they make really good gemstones. Because if you wear a ring on your finger and bells on your toe, if you've got rings on your finger with a gemstone, of course, I don't wear gemstones, but I do have a wedding band. But if you wear a gemstone and you bump into things throughout the day, you don't want it getting all scratched and scuffed. You want it to stay looking nice. So you're going to choose a hard mineral that will resist scratching. And here are 10 minerals, and we'll learn more about these in the near future when we talk about the hardness scale of minerals. Talc, number 1, a very low value because talc is very scratchable, and you can break talc very easily, and it turns into a powder called talcum powder, which is super soft and silky. Then we've got gypsum, calcite, fluorite, apatite, yum yum, feldspar, quartz, topaz, corundum, and finally diamond, number 10. And we'll learn what these numbers mean. But 10 is the highest number because 10 are the hardest minerals. All right, the next characteristic here, which can be very helpful in identifying minerals, is streak. Now, if you've ever heard that word before, you may know the popular meaning of the word streak is to, well, go around with no clothes on. We're not going to demonstrate that in the lab or the classroom, so don't worry. Please keep your clothes on. But that word streak is very important in our understanding of the chemical composition of a particular mineral, because, check this out, different minerals on different what are called streak plates, and again, we'll learn about that more tomorrow, when you rub them on a streak plate, will produce a different color. You're removing the outer covering, so to speak, or the outer coating of a mineral, and you expose the inner surface of a mineral. By doing that, you leave a rubbing of a certain colored powder behind on what's called a streak plate. So here we have two different minerals, and these minerals have different colors. Colors not necessarily all that helpful in identifying the mineral, but we can see metallic luster and non-metallic luster. But notice the different color of the streak on a dark plate or a light plate. They leave different colored streaks or powdered material behind. And that is the definition of streak. It's the color of the powder when rubbed on a streak plate. A streak plate is basically just a piece of porcelain, like a tile, like a bathroom tile, the back of it anyway. And when you rub a mineral on a rough, non-metallic or non-glassy surface, like a piece of porcelain tile, you will leave behind some colored powder. Again, that colored powder is what gives a distinctive, unique color we call streak, which can help you identify a mineral because it's more indicative of the chemical properties that make up the mineral, not just the outside color. So there we've got streak. And here's a close-up of a dark mineral here that leaves a brown streak. You know, if you just look at this mineral, you might think, oh, the streak is probably black or silver looking, but no, this one is brown because of the elements that make up this mineral. So streak is typically more helpful than just the color of the mineral. The color of the streak can help identify a mineral. That brings us to number 5. Number 5 is the density of a mineral. Now, I know you're all familiar with density from our activities in the lab last week. Density is how tightly packed particles are. There are some minerals that have densities much higher than others. For instance, diamonds have a pretty high density because the atoms are so packed together. Graphite, on the other hand, made of the same element as diamonds, but the element is not packed nearly as dense, and so its density is lower than diamonds, which is related to the hardness of the mineral as well. But density can be defined in our notes as the mass per unit volume. And again, that should sound familiar to you from last week because the mere definition or the equation of density is mass divided by volume. But in the context of a geologist, like we are this unit as we study minerals, a geologist will refer to the density of a mineral as its heft. Heft can be generally determined by picking up a mineral in your hand and holding it. And your brain automatically does a calculation without numbers, but just based on the size of the mineral and how heavy it feels. That's what heft is. I'll give you some examples of minerals that are about the same size as one another, but when you feel them, one will seem so much heavier than the other. A geologist would describe that as having more heft. It feels heavier than it appears. That's heft. So if we had a piece of gold, for instance, and here's a sample of gold, and boy, I wish I had a sample of gold this big in my palm of my hand, because gold is very, very dense. And if you were to have a specimen that big in your hand, it would feel heavier than most things you've ever felt of that size and dimension, of that volume, because gold is very dense and it has a very high heft. All right, that brings us to number 6. Number 6 is the crystal shape. You're going to be examining a variety of minerals, all of which contain different shapes. Now remember the shape of a crystal, and there are 6 basic shapes to minerals. They're based on the atomic structure of that mineral. So whatever the chemical formula is of that mineral determines the atomic structure, and it's that atomic structure which determines the basic crystal shape. Some minerals have very beautiful, uniquely shaped crystal structures. Here are some examples. Galena, which we will see, just like pyrite, produces cube-shaped crystals. Beryl and calcite, they produce other types, hexahedron crystals. Then we got some wolfenite and stibnite. These are pretty wild minerals, and they produce these column crystals that are just beyond description when you see them in natural form. Number 7, breakage. Now, let me be very careful when I talk about breakage. My mineral collection is very valuable to me, and you are going to be exploring some of my minerals in the lab on Thursday trying to identify. This is one of the characteristics you're going to use to identify a mineral. When I talk about breakage, I'm not talking about actually breaking it. So don't break any of my mineral samples, please. But breakage describes the way a mineral breaks, and we can typically see that by the surface structure of a mineral and how it has broken off of, say, a larger chunk of its mineral. So by examining the surface, not breaking a mineral, but examining how it broke previous to getting into your hands, is a good identification tool. And there are 2 ways. The first one is called cleavage. A mineral that breaks along flat, smooth surfaces is said to have cleavage. Straight lines like the stones here. Not that this is a great example of cleavage in a mineral, but flat, straight, smooth surfaces indicate cleavage. Here's cleavage in one direction. Muscovite is a good example of cleavage in one direction. Feldspar experiences cleavage in 2 directions. Halite, which by the way, there's my little cursor. Halite, by the way, which is salt, has cleavage in 3 directions. And calcite has cleavage in 2 directions, but at different angles. But all of these minerals here, if we look at the diagrams here, we can see how they have broken along smooth, flat surfaces. These are all examples of cleavage. Fracture, on the other hand, and you can think of a broken bone or a fractured bone as an example of fracture. And fracture is not something you want in your own body. But fracture is when a mineral breaks along an irregular surface. So here we see a contrast between cleavage, these flat, smooth surfaces, and fracture, these rough, angular, or even non-angular, rough, irregular surfaces. So sometimes it may take magnification, like with a stereo microscope, to really see whether you're observing cleavage or fracture. But the general difference is as I have described. And this brings us to the final property of minerals when identifying minerals: special properties. And there are a whole host of really cool special properties in identifying minerals. Minerals can either be magnetic, and you can test that by putting a magnet next to them. They could be radioactive. Put a Geiger counter up to it. We might be testing these, by the way. Odor. Some minerals stink and you will smell it. Some mineral like sulfur really stinks, like a scratch and sniff sulfur. Ooh, you can tell it's sulfur. Now, we're not going to taste anything in the lab, but some minerals like halite, for instance, salt, have a salty flavor, but we're not going to taste any. Some of them glow, like the ones I showed you yesterday, the fluorescent minerals. And some minerals are chemically reactive, meaning if you add them to different chemicals, say hydrochloric acid, put a drop of hydrochloric acid on it, it could cause a chemical reaction. We may see some things like that in the laboratory this week. Now, I've given you a lot of information, some properties of minerals, as well as how to identify minerals here today. So we're going to call it quits for our notes. We'll save the rest for tomorrow. And so until tomorrow, I'm going to say bye-bye.